All right, thank you. Can you guys see the screen?
Yeah, it looks great.
Okay. All right, so yes, as Randy said, I'm going to be presenting on some of our fuzzy clustering products that we are developing here at WPC. And I've sort of framed them as a complement to the NBM, so something you can use in concert with the NBM when you're making a forecast. So I'm just going to start with some of the motivation of the meteorological problem that we're trying to solve with these fuzzy clustering tools. And that is that the atmosphere is a chaotic system, so forecasting the weather, especially at longer lead times, requires the use of ensembles as they can show the uncertainty and also the range of possible forecast scenarios. However, ensembles also pose challenges to the forecaster in that they contain a wealth of information about the forecast, but it can be hard to see the signal through the noise. And also, forecasters may not have time to thoroughly look at the ensembles if they're working under time constraints. So this is where WPC's fuzzy clustering products can help. And just to kind of illustrate this, I have a figure here which just shows the 168-hour GEFS forecast of 500 millibar heights. This is from several years ago, but it's just the spaghetti plots that a lot of people are used to looking at. And in this particular plot, you just see kind of a lot of lines going everywhere, so it's just illustrative that it's kind of hard to see the signal through the noise with some of these ensemble products that we currently use. So what is fuzzy clustering? So fuzzy clustering is a way to partition the members of an ensemble into groups of members that have similar forecasts. And it has two key benefits to the forecaster. First, it can help forecasters quickly assess where the greatest uncertainty in the forecast is. And then second, as I said before, it can help solve that age-old problem of so many ensemble members, so little time. So if you don't have time to look at all 90 ensemble members of the GEFS, European, and Canadian ensemble, fuzzy clustering can help simplify the onslaught of data by distilling the ensemble down into the few forecast scenarios that predominate in the ensemble. So how should you use these fuzzy clustering products? So as I said earlier, we're kind of framing them as a complement to the national blend of models. So the NBM does combine ensemble data and turns it into a forecast, so both deterministic and probabilistic. But the NBM is a bit of a black box, and it doesn't necessarily show forecasters the range of possible forecast scenarios. So you don't necessarily know what's going into it, and you don't get a clear picture of the range of forecast scenarios. And WPC's fuzzy clustering tools let forecasters dive into the ensemble data to better assess the forecast uncertainty and the range of possible forecast scenarios. And I think our fuzzy clustering tools are best shown with an example. So today we're going to go through and apply fuzzy clustering to the 6-day forecast for this Saturday's upcoming precipitation and temperatures in the Central Plains. Because as I'm sure you guys are aware, there's a pretty big storm and high impact weather event that will be impacting the central and eastern United States this weekend. So for applying fuzzy clustering, I just put up a quick recipe here, which is the steps that we're going to go through. So first is you have to calculate and interpret the first two empirical orthogonal functions, or EOFs, of the 500 millibar height forecast over central region from the global ensembles, which we are just defining as the European ensemble, the GEFS ensemble, and the Canadian ensemble. I know there's some more ensembles that are out there, but here at WPC, those are the three systems that we have access to, so that's what I will be using. And then next, you use the k-means clustering algorithm to create clusters of ensemble members based on their principal components for the EOFs. And then finally, the last step and the most important step is to physically view the clusters to see what they're showing. So again, we're going to apply fuzzy clustering to the 6-day forecast for Saturday's precipitation and temperatures in central region. So just to kind of, I'm sure you guys are aware of this upcoming storm, but just to kind of orient you, here is the current NBM forecast for this Saturday. You can see a lot of heavy precipitation is being expected to fall in the central and eastern United States, a general 1 to 2 inches. And then also, if we look at the temperatures, it's going to be pretty chilly behind that system, a lot of single digits in the upper Midwest, but also pretty warm out ahead of it with a lot of 60s and even some 70s just to the west of the Appalachians here. But I want to draw your attention, at least on the precipitation forecast here, to sort of some of the precipitation amounts that are being forecasted in southern Michigan and central Illinois. Because if we go and look at the NBM forecast that was created on 5 January or 6 days prior to the event, we can see that the forecast was a lot less in these areas. Generally, nothing to maybe 0.2 of an inch, whereas now they're forecasted to get an inch or more of precipitation. Also looking at the temperatures, especially if we look here over eastern Kentucky, where the current forecast is now for temperatures in the 60s to maybe even low 70s. On January 5th, the NBM was just predicting temperatures to be much cooler, a lot of 50s and maybe low 60s. And then looking kind of here in southwestern Minnesota, the forecast from 5 December was forecasting temperatures in the upper teens to low 20s, whereas now the NBM is much cooler and it's looking more like single digits to lower teens. So that's basically been the trend of the forecast over the last few days, is to push that precipitation further to the north and to the west, and also kind of get some cooler temperatures in the upper Midwest, but also warmer temperatures out ahead of the system. So that's been the trend. So now we're going to apply fuzzy clustering to kind of show you what you could have seen from the ensemble forecast 5 days or 6 days prior to this event. So again, I have the recipe up here. First, we're going to calculate and interpret the first 2 EOFs of the 500 millibar height pattern over central region from the global ensembles. Then we're going to use the k-means clustering to create clusters of ensemble members based on the principal components for the 2 EOFs. And then finally, we're going to view the clusters. So just a note on EOFs for those who may be unfamiliar with this data analysis technique, but basically it is a data analysis technique that is often used in climate studies as a method for determining the spatial patterns that most efficiently explain the variability of a multivariate data set. So in other words, what patterns are most common in the data set. And for example, it's how we get teleconnections like the NAO. So for example, the NAO is the first EOF of sea level pressure over the North Atlantic. And most EOFs are in general calculated over time like the NAO, but however, if you calculate the EOFs over a model ensemble member dimension as opposed to the more conventional time dimension, you will get modes that show the dominant patterns of the differences between the individual ensemble member forecasts and the ensemble mean. And then also for each EOF, each ensemble member will have a principal component. And so just a note on principal components, if you're unfamiliar, principal components are the projections of the dominant EOF patterns onto the difference between each of the ensemble members and the ensemble mean. So just an English translation, an ensemble member with a large principal component for an EOF pattern will resemble the ensemble mean with that EOF pattern added to it. So basically it's a lot of math, but as I'll show you later, you don't really need to know the math in order to interpret and imply the results of the EOF analysis. So for today's presentation, we're just going to calculate the EOFs of the 500 millibar height field over central region on day 6. So 0Z on the 11th of January to 0Z on the 12th of January from the ensemble forecasts that were initialized at 0Z on the 5th of January. And that's what I have on this slide here. So we have these 2 panels here. On the left, or in both panels, what's contoured here is the ensemble mean of all 90 ensemble members for the geopotential height field for Saturday. And then the color shading is the actual EOF pattern. So if we look at this first EOF here, which is on the left, it explains 38.3% of the variance in the 500 millibar height forecast for Saturday. And so we can see, looking at the ensemble mean contours, we can see it's kind of hard to see, but there's a weak trough over the central United States and then a downstream ridge over the eastern United States. So we have this trough ridge couplet. If we look at the EOF pattern, which is the shading here, we see lower values to the east and higher values to the west of this trough right here. So what that's telling us is that you can kind of imagine, heights being lower in this area and heights being higher in this area. So in general, just a shifting to the east of this trough ridge couplet. So with EOFs, the sign is arbitrary. So you could also just kind of flip the sign on this and say you could also lower heights to the west over the southwest here and raise heights to the east over the eastern United States. And in this case, the shift would be to shift that trough ridge couplet further to the west. So basically what this first EOF is showing us is that the dominant mode of uncertainty in the forecast over the central United States for this day is the east-west location of this trough ridge couplet. So looking at EOF2, this time the EOF pattern is kind of co-located with the axis of the trough and then, or at least the crest of the downstream ridge. So you can imagine lowering heights in this location and raising heights in this location. So what this EOF is telling us is that the second mode of variability in the 500 millibar height forecast over a central region for this date is the amplitude of this trough ridge couplet. So that's basically what I've shown here. So EOF1 tells us that there is considerable, i.e. the most uncertainty in the east-west location of the 500 millibar trough ridge couplet over the central region. And then EOF2 tells us that there is also uncertainty in the amplitude of the 500 millibar trough ridge couplet over central region. So next, what you can do is, as I said earlier, each ensemble member will have a principal component for those two EOFs here, which tells you how much that ensemble member resembles that given EOF pattern. And that's what we have here. Is we have the principal components along the x-axis for EOF1 and the principal components for EOF2 along the y-axis here. And I have all 90 ensemble members from the Canadian, the GEFS, and the European ensemble plotted on this PC1, PC2 phase space, where the red shows the Canadian ensemble members, the green shows the GEFS ensemble members, and the blue is the European ensemble members. And just to kind of orient you, I have put in here on text boxes just to kind of show you what ensemble members say in this part of the phase space. These ensemble members have that cluster or have that couplet further to the east. The ensemble members that are over here have that couplet further to the west. The ensemble members down here, which have a negative principal component for EOF2, have a less amplified couplet, whereas the members up here have a more amplified couplet. So I've already gone through and clustered the 90 ensemble members into 4 clusters here, but how I did that is with the k-means clustering algorithm. And so just to note on the k-means clustering algorithm, again, it's a lot of math, but all you need to know is that it's an algorithm that groups 2-dimensional data so as to minimize the distance between each point and the center of the cluster it's assigned to. So the number of clusters need to be specified beforehand. We are using 4 clusters, but in general, 3 to 5 clusters is appropriate. So here's the phase space again with all the ensemble members that are basically broken up into the 4 clusters. And again, if we look at cluster 1, these are basically all the members right here, which are in this part of the phase space. So the predominant thing that they have in common is that their principal component for EOF1 is positive. So in general, these ensemble members, we would expect to have that trough ridge couplet further to the east. So that's the physical interpretation for cluster 1. It has that couplet further to the east than the ensemble mean. So looking at cluster 2, which is the circles with the X's in them, they're over in this part of the phase space. So the main thing they have in common is that their principal component for EOF1 is negative. So basically the reverse of that. Cluster 2, the physical interpretation is that it has the trough ridge couplet further west than the ensemble mean. Looking at cluster 3, which is the diamonds, they are down here in this part of the phase space. So the physical interpretation for this, having that principal component for EOF2 being negative, is that the couplet is less amplified in this cluster. So that's the physical interpretation for cluster 3. And then finally for cluster 4, which are the triangles, they're mainly up here in this part of the phase space, corresponding to that couplet being more amplified. So again, that is the physical interpretation for cluster 4, having that couplet being more amplified. So that's how we get the clusters, but now this is the most important part, which is actually viewing the clusters. So what I have here on this 5-panel chart, it's the cluster mean for each of the 4 clusters, as well as the total ensemble mean, which is down here in the bottom right. And in each of these figures, what's contoured is the cluster mean 500 millibar heights, and then the anomalies are in the color fill. Now, in each of these charts at the top here, we have a C, G, and E. So the numbers right next to each of those just tells you how many ensemble members from each ensemble prediction system are in this cluster, and then the percentage of ensemble, or the percentage of that cluster, or sorry, the percentage of that ensemble prediction system that is in that cluster. So for example, if we look at cluster 1, we can see that there are 6 Canadian members, which is 30% of the 20 overall Canadian ensemble members. There are 9 GEFS members, which is 45% of the GEFS ensemble, and there are 11 European ensemble members, which is 22% of the European ensemble. So for a total of 26 members, or 29% of the 90 ensemble members that we're looking at. So just in the green text here, I've written down there what the physical interpretation for each cluster is, but really that's self-evident if you just look at the cluster. So for example, cluster 1, which had that trough ridge couplet further to the east, if we compare this to the total mean down here, we can see, especially if you look over Illinois and Indiana here, that ridge is definitely further to the east. Looking at cluster 2, the physical interpretation was having that trough ridge couplet further to the west. And again, if you compare this to the total ensemble mean, you can see indeed that trough ridge couplet is shifted to the west a little bit. Looking at cluster 3, the physical interpretation of that was for the trough ridge couplet to be less amplified. And again, if you compare this to the total ensemble mean, obviously the differences are a bit subtle, but you can see the trough, it's not quite as deep. And also the downstream ridge, especially on the northern periphery of it, it is not as amplified. Whereas cluster 4, the physical interpretation was to have the trough ridge couplet being more amplified. And again, just by looking at the height pattern, you can see that clearly. This trough here, a lot more below normal heights, as well as the downstream ridge. It's definitely more anomalous, especially on the northern periphery of the ridge there. So this cluster is clearly more amplified with that ridge. So we get the clusters by looking at the 500 millibar heights, but we really are concerned with the surface variables, so precipitation and maximum or minimum temperatures. So what we can do is we can take the cluster membership from the 500 millibar heights and then look at cluster means for those variables. And that's what I have on the next slide here. So again, we have all 4 cluster forecasts as well as the total ensemble mean. In this plot, the cluster mean QPF is contoured, and then the color shading in this particular plot is the difference between each cluster and the total ensemble mean. So you can kind of see quickly how this cluster differs from the mean of all 90 ensemble members. So if we look quickly just at cluster 1, which was having that trough ridge couplet further to the east, it makes sense. Basically, it has wetter conditions further to the east and drier conditions further to the west, with those the greenish colors indicating, more precipitation than the total ensemble mean, and the reddish brownish colors are less precipitation than the total ensemble mean. So we can see having that trough ridge couplet being further to the east basically moves the precipitation shield in the storm track further to the east. Cluster 2, which was west with that trough ridge couplet, as you can imagine, basically it has the heavier precipitation further to the west. Looking at cluster 3, which was less amplified with that trough ridge couplet, you can see it has heavier precipitation basically aligned along the axis of where we expect the most precipitation. So it's increasing amounts along the axis of expected heaviest precipitation. But since it's not as amplified, it's not able to pull that moisture further to the north. So we can see it's really cutting down with precipitation amounts on the northern periphery of the storm system. Whereas this here in cluster 4, which was more amplified with the trough ridge couplet, you can see that basically the opposite. It's able to pull a lot of that moisture further to the north, and we see heavier precipitation amounts up to over an inch, kind of in that northern Illinois to southern Michigan corridor. So that was the precipitation, and now we can also look at the same thing with temperatures. So these are maximum temperatures for Saturday. And again, what's contoured here is the cluster mean for each of the 4 clusters, as well as the total ensemble mean. And then the color shading is the difference between each cluster mean and the total ensemble mean. So again, you can kind of see quickly how that cluster differs from the mean of all 90 ensemble members. As expected, this cluster here, which had that trough ridge couplet further to the east, basically has the cooler temperatures being able to spill further east more quickly behind that front. So it's about maybe 4 to 6 degrees cooler in the upper Midwest. Whereas if we look at this cluster here, which was further west with that trough ridge couplet, we can see it's bringing some of the warmer conditions further northward and further westward, because that basically the front is located further to the west. Looking at this cluster here, which is less amplified than the total ensemble mean here. So basically, it's just less amplified. It's not as cool back where we are expecting cooler conditions, and it's not as warm out ahead of that front, indicating a less amplified system. Whereas down here with cluster 4, that was more amplified, and we can see it's definitely cooler. We're expecting the cooler weather and also warmer out ahead of that front, indicating a more amplified system. And again, this just relates back easily to the 500 millibar heights. And that's why we do our clustering based on 500 millibar heights, because that's a nice variable to cluster on, and a lot of, 500 millibar height tends to set where the storm track is going to be. So that's why we do our clustering on the 500 millibar heights, and then we kind of let the other variables such as QPF and precipitation fall out from our 500 millibar height clusters. So putting this all together, so the EOFs of 500 millibar geopotential height show that the main uncertainty in the forecast is the location and amplitude of the trough ridge couplet over central region. So the ensembles are keying in on a few possible forecast scenarios for this trough ridge couplet, and viewing the clusters shows a forecaster how differences in the location and amplitude of the trough ridge couplet affect the forecast for precipitation and temperatures over central region. Also, viewing and interpreting the EOFs and the PC1, PC2 phase space can be complicated, but it's not necessary in order to use our clustering products. So the physical interpretation of the clusters will be self-evident when you view them. So you don't need to look at the EOFs. While that's nice to look at the EOFs and kind of go through and interpret the phase space like I did, it's not necessary. So to just illustrate this, we're going to apply fuzzy clustering to the 4-day forecast, again, for Saturday's precipitation and temperatures in central region. So here's the NBM forecast from yesterday, so 4 days prior to the event. You can see it started to increase precipitation amounts basically in that corridor from central Illinois to southern Michigan. So they're now about an inch of rainfall is being expected. And again, it started to warm up temperatures ahead of that front, but also cool temperatures a little bit further behind the front. So we're not going to go through the EOFs and the phase space. We're just going to look at the clusters. So this is what we have. It's initialized on 7th of January, and these are the 500 millibar height clusters. So just comparing them to the ensemble mean, we can see the differences are subtle, but this one is a little less amplified with the trough and downstream couplet. So this cluster here is a little less amplified. This cluster here is maybe a little bit more amplified. We can see some lower heights to the west here and some higher heights, especially on the northern periphery here. So this cluster is more amplified, whereas this cluster here, it's definitely a bit further to the east with the trough ridge couplet, and this one is definitely a bit further to the west. So that's the physical interpretation, and you'll see if we look at the QPF forecast on the next page, a lot of the interpretations are similar to the forecast that was made on the 5th of January. So this cluster here, which was less amplified, we can see it's cutting down on precipitation amounts on the northern periphery of the storm. This cluster here, which was more amplified with the trough ridge couplet, is definitely increasing precipitation amounts on the northern periphery here, well over 1.5 inches of rain being expected from that central Illinois to southern Michigan corridor. This cluster here, which was further to the east with the system, you can see basically trimming back on precipitation amounts basically to the west and increasing them to the east. And then this cluster here, which had the trough ridge couplet further to the west, it's basically increasing amounts along the western periphery of the storm and decreasing them on the eastern periphery of the storm. So again, you can get all that without looking at the EOFs in the phase space. And same thing with temperatures. This cluster here was less amplified, so we can see it's not as cool back behind the front, but also not as warm out ahead of the front. This cluster here was more amplified with the trough ridge couplet, so you can see it's cooler behind the front and also warmer out ahead of it. This cluster was further east with the trough ridge couplet, so you can see it's got some cooler temperatures being a bit further to the east, kind of having that front further to the east. Whereas cluster 4 was further to the west, and we can see it has basically that front in this area with a strong temperature gradient just being pushed further to the west. So just to summarize and give the relevance to operations, so a forecaster coming into work 3 to 7 days prior to Saturday could view the 500 millibar height EOFs and immediately see that the greatest uncertainty in the forecast for Saturday was the location and amplitude of the central U.S. trough ridge couplet. Viewing WPC's fuzzy clustering products would help them see how differences in the large-scale pattern affect precipitation amounts and temperatures over central region. And I think that this is useful information when you're making and communicating a forecast and also the possible ways that it could play out. And this is information that the NBM does not provide. So if you guys are interested, a lot of the fuzzy clustering products that I've shown here are available on the web. So for the day 3 to 7 CONUS weather clusters, you can go to this website here. We also have day 8 to 10 CONUS weather clusters, again, for maximum temperature, minimum temperature, and QPF. They're located at this website here. And we also do fuzzy clustering more in the shorter range for our winter weather experiment. So we do day 2 and day 3 winter weather clusters, and they are available here. If you're interested in learning more about the fuzzy clustering methodology, I highly recommend this paper here, which is by Brian Colley and some of his colleagues at the State University of New York at Stony Brook. They did a lot of the pioneering work with fuzzy clustering, and I've sort of taken their methodology and kind of applied it to basically our forecast challenges that we have here at WPC. And so with that, I will take any questions or comments.
Thanks.